We're given the following series from n equals 1 to infinity, n cubed over n to the fifth plus 3. First thing to always check is, does the limit go to 0? And in this case it does. Then we want to see, well, does this look like it's going to converge or diverge? So the way we're going to check is to look at the sequence. N cubed over n to the fifth plus 3 in the long run is basically n cubed over n to the fifth, which simplifies to 1 over n squared. We know by the p-test this is going to converge. So let's use a direct comparison, and you want to compare it to something bigger. If something bigger converges, then something smaller will converge. So how do you make this bigger? Well, you can make the denominator smaller. So we can remove the plus 3, and so we would just have n cubed over n to the fifth, which simplifies to 1 over n squared. This is definitely bigger, and this converges by the p-test, so then something smaller will converge. And so thus we say that the sequence converges by the direct comparison test. Next example, we're given the sum from n equals 1 to infinity, 3 to the n over 4 to the n plus 1. 4 to the n plus 4. Okay, so we know that in the long run, this is basically 3 to the n over 4 to the n, which we can factor out the exponent and just have 3/4 in here. So the ratio is 3/4, and it's between -1 and 1. Therefore, we would expect this to converge. So let's use a direct comparison test, and let's find something bigger. The way to make this bigger is by removing, or by making the denominator smaller. So we're going to remove the plus 4, and we're going to have 3 to the n over 4 to the n, which we can factor out the n and just have 3 over 4. This converges because it's a geometric series with a common ratio between -1 and 1. And so by the direct comparison test, we would expect something smaller to converge. And so the series converges. The last example, we're given the sum from n equals 1 to infinity of 1 plus 2 to the n over 3 to the n minus 1. We want to actually find the sum of this. Okay, so the way we're going to do this is to break it up into two pieces. We have 1 over 3 to the n minus 1 plus 2 to the n over 3 to the n minus 1 from n equals 1 to infinity. So the first one, I guess we could break it up into two different ones. So, from n equals 1 to infinity, 1 over 3 to the n minus 1, and sum from n equals 1 to infinity, 2 to the n over 3 to the n minus 1. This is an infinite geometric series, so for an infinite geometric series with a common ratio between -1 and 1, we know that the sum is the first term divided by 1 minus the ratio. So starting with the first series here, the first term is when n equals 1. Plug it in. We have 1 minus 1 is 0, so it's 1 over 3 to the 0 power, which is 1. Divide that by 1 minus the common ratio. The common ratio is basically the number that is being raised to the exponent, and here it's 3. But because it's in the denominator, it's going to be 1/3. Plus, now with the second sum, the first term is when n equals 1. So you have 2 over 3 to the 0, which is just 2. And it's 1 minus the ratio. Well, the ratio is whatever is being raised to the n power, which here it's 2 and 3. So the ratio is 2/3. And now we could just simplify this. and 1 minus a third is 2/3, and then 1 minus 2/3 is 1/3. So 1 over 2/3 is really the reciprocal of 2/3, which is 3/2. And then 2 divided by 1/3 is basically 2 times 3, which is 6. So it's 3/2, which is 1 1/2, plus 6 will give us 7 1/2. And that is our sum.